All right, let's talk about a word you hear everywhere these days, algorithm. You might think it's some super complex thing just for tech gurus and coding wizards, but what if I told you that you already use algorithms all the time, every single day? Let's break it down. So let me ask you this. Have you ever followed a recipe to bake a cake? You take the exact amount of flour, you mix the eggs in at just the right time, you preheat the oven to a very specific temperature. Or how about this one? You've got that flat pack furniture and you're staring at the user manual, following those little diagrams step by step to build it. You connect part A to part B, then screw in part C. Well, if you've done either of those things, guess what? You've already used an algorithm. That's really all it is. It's just a set of clear, ordered steps to get something done. And they are absolutely everywhere. So here's what we're going to cover. First, we'll nail down what an algorithm actually is. Then we'll look at its basic structure. We'll explore two ways to map them out, with drawings called flowcharts and with text called pseudocode. And finally, we'll talk about why thinking this way is such a game changer. All right, first up, let's get right to it. What is an algorithm? Really? Now, this definition might look a little formal, but it's exactly what we were just talking about. Just think back to our cake recipe. It was a set of defined instructions. Add 2 cups of flour. It was ordered. Mix the dry ingredients before the wet. And it was finite. It ended when the cake came out of the oven. Simple as that. And for any algorithm to actually work, it has to have these 3 qualities. It's got to be precise. Each step has to be crystal clear. No guessing. It has to be defined, which means if you use the same recipe with the same ingredients, you get the same cake every single time. And finally, it's got to be finite. It has to stop. It can't just run on forever. And here's the really cool part. It doesn't matter if you're talking about a simple recipe or the complex code that guides a self-driving car. Every single algorithm shares the same basic 3-part structure. It all boils down to this. You start with an input. That's your ingredients, your data, the stuff you're working with. Then you apply a process. That's your set of instructions, the steps you take. And what comes out at the end? That's your output, the result. Input, process, output. That's the backbone. Let's make this super concrete. Think about calculating a paycheck. The inputs are the raw numbers. Your pay rate, the hours you worked, the number of days. The process is the math you do, multiplying it all together. And the output? Bam! Your total salary. It's a logical, repeatable flow. Okay, so we know what an algorithm is, but how do we plan one out or explain it to someone else? Sometimes the easiest way is to just draw a picture of it. And that's where flowcharts come in. Think of flowcharts as a universal visual language. They use a standard set of symbols, so anyone can look at the diagram and immediately understand the logical flow of the process. So let's learn the basic vocabulary, the 4 most common symbols. First up, we've got the oval. Some people call it the terminator. It's super simple. It just marks the start and end of your entire process. It tells you where things kick off and where they wrap up. Next is the parallelogram. This one is all about input and output. Think of it as the gateway where data either enters your system or exits it. This ties directly back to our input, process, output structure. Then you have the good old rectangle. This is your process box. It's the workhorse of the flowchart. Anytime an action, a calculation, or an operation happens, it goes inside one of these. This is where the work gets done. And finally, the diamond. This is where your algorithm gets smart. It's a decision point. It asks a simple question that has a yes or no answer, and based on that answer, the process can split and go down 2 completely different paths. This is how algorithms make choices. And this visual language is incredibly versatile. I mean, look at this. On the left, a flowchart that maps out a physical task, the steps to change a flat tire. On the right, a totally different chart, mapping out abstract logic for a computer to compare 2 numbers. Different worlds, same symbols, same clear logic. So, if a flowchart is the visual blueprint, what's next? Well, sometimes you need something that gets you 1 step closer to what a computer can understand. And that's where we get pseudocode. Think of it as the bridge from our human idea to the actual code. So what's the difference here? While a flowchart is your visual map, pseudocode, which literally means false code, is a text-based outline.
It's this cool blend of plain English and programming structure. It's perfect for quickly hammering out the logic before you get bogged down in writing real, syntactically perfect code. Let's look at this example. We need to find the largest number in a list. The pseudocode is really easy to follow, isn't it? It basically says, okay, let's start by assuming the first number is the maximum. Then we'll go through every other number one by one. If we find a number that's bigger than our current maximum, then that becomes the new maximum. You just keep doing that until you've checked them all. It's readable, but it's also perfectly logical.
Okay, so we know what algorithms are, we know how to draw them, we know how to write them, but here is the biggest takeaway of all. This isn't just about computers. Learning to think this way, it's like unlocking a mental superpower. Steve Jobs absolutely nailed it with this quote. Learning to program isn't just about the code itself. It teaches you how to think. And that's it, right there. Structuring your thoughts like an algorithm, breaking down a big, messy problem into small, logical, manageable steps, is a skill that you can apply to everything. Ultimately, when you think this way, it just changes the game. It brings clarity to confusing problems. It helps you explain your ideas so other people can actually get on board. You can spot potential issues and bottlenecks way before they become big problems. It gives you a reliable framework to solve, well, pretty much any problem.
So the next time you're facing a challenge, whether it's planning a vacation, organizing a project at work, or even just trying to clean out your garage, try it. Break it down. What's your input? What's your process step by step? And what's the final output you're aiming for? Now that you can think in algorithms, what problem are you going to solve first?